During the last lecture, I went over how to break things into components, and I did mention that it was a lot easier than using the parallelogram rule, although the component method is actually an application of the parallelogram rule. You may be wondering, why on earth then would anyone ever use the parallelogram rule when the method of components is so much simpler? And the answer is given in this particular example. You'll notice in the given diagram that we have two different vectors, the 20 kilonewton and the 40 kilonewton force. You'll also notice that the axes, u and v, are given. These are not the x and y axes. They're not your standard 9 degrees apart, nor are they on horizontal and vertical. And why would you ever want to do this? Well, rotating axes is done at times to figure out components that are within machines, for example, or when we're dealing with friction. Sometimes the surface is in an incline, and so it's advantageous to rotate the axes. And when you have non-standard axes that are not 9 degrees apart, you have to use the parallelogram rule. In this case, I'm still going to break the vectors into their resultant components, but this time I'm going to use the parallelogram rule to do so. A working diagram does need a sign convention, and since this particular diagram doesn't have your standard x and y axes, that becomes all the more important. Anytime that your axis system is not the standard x horizontal, y vertical, you need to say how far the axes are apart in degrees and also how far they are rotated off of the horizontal. In this case, the u axis, so I'm going to define this direction as positive u, is on horizontal. I'm going to define this direction as positive v. Now, if we look at our two axes, there's 90 degrees between this vertical line and u, and there's 20 more degrees between the vertical line and v, so that's a total of 110 degrees. And that would have to be marked on our sign convention. In order to break these into their u and v components, we have to project them onto their respective axes. Take F1 and project it onto the v axis. We would take the u axis and slide it over to right there. Likewise, we would take the v axis and slide it over parallel to right there. So now this vector that I will draw along the v axis, this is F1v, this is F1's u component. We'll take F2 and slide it over to the u axis. We'll take F2 and slide it over to the v axis as well, projecting those axes. Make sure that your projection lines are parallel, so you notice that the projection line here from F2 to the v axis is parallel to u, and the projection line here from F2 to the u axis is parallel to v. This component here is F2's u component, and this component here is F2's v component. Now, before I continue this problem, I also need to define these angles. So this 60-degree angle right here is my alpha. Now, if we look over at the other angles, from here, from this F1 to the vertical line would be 30 degrees, and if you remember, from the vertical line to the v-axis is 20 degrees. So that means that this angle here, beta, is going to be 50 degrees. If we use our triangle rule, we know that there's going to be 180 degrees within a triangle. So that means that this angle over here, which I'll call delta, is 70 degrees. Over on the other side, this 25-degree angle between v and F2u, I called that epsilon. This angle right here is 25 plus 20 degrees, so that's 45 degrees from F2 to the vertical axis, which means that this angle here is also 45 degrees. And I called that phi. This large angle here that is theta. This last angle is 110 degrees. So after we've got our working diagram and all of our dimensions on there, now I'm going to go ahead and solve for my F1 components. So I'm going to say solving for f1u and f1v using law of sines. So using the law of sines, we have a side divided by an angle equals another side divided by another angle. So if I were to say f1u, I'm going to start with that one. f1u is this piece right here. The angle opposite is straight up, which is my beta angle. So f1u divided by the sine of beta equals f1, because that's our known, and the angle opposite from f1 is delta. So now I need to take that equation and rearrange it to solve for f1u by itself. So f1u equals sine beta times f1 divided by the sine of delta. So f1u, now we've got our equation with our variables, we can now put our equation with our numbers. Sine of beta was 50 degrees times f1, which is 40 kilonewtons. Divided by the sine of delta. So that's the sine of 70 degrees. And we find that f1u equals 32.6083 kilonewtons. And if we look at our sign convention, f1u is going towards the right, which I have defined as positive. Now, alternatively, you could show a vector symbol showing that it's going there to the right, but you cannot do both, as I've said before. And in this case, I'm going to use the positive sign. Likewise, we're going to solve for f1v. f1v divided by its opposite side angle. So here's f1v, the opposite angle is up here, which would be alpha. Equals f1 divided by the sine of delta. So that means that f1v equals the sine of alpha times f1 over the sine of delta. If you can go straight to the second step, you are not required to write the first step. Remember, your minimum requirements are equation with variables, equation with numbers, answer. So really you just need this line and what follows. If you feel more comfortable writing that first line like I am, that's totally fine. So f1v equals the sine of 60 degrees times 40 kilonewtons divided by the sine of 70 degrees. So f1v equals 36.8642 kilonewtons. Once again, that is in the positive direction. So now I've got both of our f1's components. So this is going to be step 3. And I'm going to say solving for f2u and f2v using law of sines. Let's take a look at f2. We'll start with f2u. f2u. Now we need to look at the angle that's opposite of f2u. So f2u is down here, it's this little one on the bottom. The angle opposite's the angle that doesn't touch it. Not theta and not phi, but rather epsilon, which is up here, or the opposite interior angle is over here. So that's f2u divided by the sine of epsilon equals F2. This is the law of sines. The angle opposite F2 is theta, this large angle, sine theta. So rearranging and solving for my unknown gives me F2u equals the sine of epsilon times F2 divided by the sine of theta. Now plug my numbers in. The sine of 25 degrees times F2, which is 20 kilonewtons, divided by the sine of 110 degrees. And F2u is going to equal an 8.99482 kilonewtons. Now you'll notice it's going in the opposite direction as what I've defined as positive u, so that is a negative. Now we'll need to solve for F2v. Looking at our triangle, F2v is up here on this side of the triangle or parallelogram. The opposite angle is over here, which is phi. And that equals F2 divided by the sine of theta. So F2v equals the sine of phi times F2 divided by the sine of theta. Phi was 45 degrees. F2 is 20 kilonewtons, and theta is 110 degrees. So that means F2v equals 15.0497 kilonewtons, and it's going up, so that means it's positive. It's going up and towards the left. Now before I go on, I do want to note that although when we have right angles, the x and y axes are 90 degrees apart, the resultant, or the diagonal, will always be longer than the components. When we have non-standard axes, such as this, it is possible to have components that are actually larger than the resultant vector. So it's possible that I would have found F2v not with this particular set of angles, but I could have changed the axis orientation and made it such that F2v is actually larger than F2. For our last step, we're going to combine the components, and we're going to say solving for FRU and FRV. Once again, I reserve FR for the resultant. That is not required. These are all variables, and you can really call them whatever you want. But as I've mentioned before, I have a system that I go by, and I always do the same thing. I encourage you to find a system that works for you. So FRU equals F1U plus F2U. Now when we plug these values in, we have to make sure that we include the signs. So FRU equals, F1U was a positive 32.6083 kilonewtons. F2U is a negative 8.99482 kilonewtons. So when we solve these, FRU is going to equal a positive 23.6135 kilonewtons. Now next is FRV. FRV equals F1V plus F2V. FRV equals F1V was 36.8642 kilonewtons, a positive, and F2V was a positive 15.0497 kilonewtons. So that leaves my FRV equaling a positive 51.9139 kilonewtons. So now we've got our components, and we'll put those in the answer box. You might wonder, okay, well, we've got our components, what would we do next? If you were going to take these and put them back together, you would redraw another diagram, a working diagram, and put FRU and FRV in their respective locations on the U and V axes. And then you'd use the parallelogram rule again to put them back together. I'm not doing this in this example because it's exactly the same thing we've already done, so you know how to do it at this point. And that is how you work with rotated axes. Everything in Homework 5 has non-standard axes, and so you'll have to use this parallelogram method to do that. I strongly encourage you to make sure that your diagrams are large enough. This diagram is actually approaching too small. One thing that you might consider doing is making a separate working diagram for each vector. So I could have, for example, had working diagram A be just F1 and its U and V components, and then made working diagram B with F2. I would have been able to scale F2 a little bit larger there so I could see the angles a little better.